Okay, so last time I spoke about this Gauss quadrature, and today I'm going to be talking about a different aspect of orthogonal polynomial. You see, when you are dealing with orthogonal polynomial, you have basically several different ways of. So, for example, they are what are called, we started doing the following, that is orthonormalization of 1x, x squared, etc., given a weight function wx and an interval a to b. Okay, so this is one way of doing it. This is what we have been doing so far. Another way of doing it is what is called Rodrigues formula. Something I'll deal with now. And a third way of dealing with it is as solutions of differential equations. They're all equivalent. And a fourth way of doing it is what is called using generating function. This also you use it to quite an extent, particularly in quantum mechanics, when you want to have multipole expansion and so forth. Okay, in electrodynamics, multipole expansion in electrostatics, and then for various calculations, you want to do some quantum mechanical integral evaluations, then you will do this generating function. Now let me come to the Rodrigues formula. The Rodrigues, we have what is a generating. This generating function, which gives me a series expansion of orthogonal polynomials. I do not know whether I'll have time to deal with it, but you can look it up in the books. So generating function, let us say G n of x for nth degree polynomial. Then what we have in the Rodrigues function, Pnx as equal to 1 upon Wx dn by dx. Gn of x. Okay, so if you have n equal to 0, 1, 2, etc. So you can have first degree polynomial, so on and so on. Now, in order to get an equation for actually determining Gn of x, what you will see is Gn of x is a polynomial of degree n. Therefore, dn plus 1 by dx Pn of x is equal to 0, right? Because if you take a polynomial, if you take x3 power n and differentiate it n plus 1 times, it's going to give me 0. Because when you differentiate it n times, you get a constant, which is n factorial x, differential of n factorial with respect to x is 0. Okay, so what happens is that if you put this differential equation, then what you have is a condition that dn plus 1 dx for n plus 1 by w of dn by dx over n dn x is equal to 0. So this is a differential equation of order 2n plus 1. Because what you will see is that you are differentiating Gn of x effectively 2n plus 1 time. So if you want to have a solution for this which is particular, then we need 2n boundary. Actually, one condition normally. So that is okay. So you have 2n plus 1 conditions. If one condition is lower than remaining 2n conditions have to be. So these conditions are going to be the following. You can say that G A equal to G prime equal to G to the power equal to 0. So this is n conditions at one boundary point, which is A. The other boundary point is B. B equal to G prime B equal to B, etc. Equal to Gn B. So Gn is actually in this case Gn is equal to D G by D Dn G by dx. Okay, so that means we are differentiating. So let me put it as Gn so that we don't have a problem. Okay, so let me put that. So, so there is Gn n minus 1. So because from 0 differentiation up to n minus 1 differentiation, you have got n conditions. So it's actually all the differentials up to the n minus 1th differential of Gn are 0 at the two boundary points, A and B. So if you have this condition, then I can show that any A to B and x or W dx is equal to 0 if is of less than or equal to n minus 1. So this is the condition for orthogonal polynomials, right? Because an orthogonal polynomial Pn of x is 1, which ensures that it is orthogonal to all polynomials of degree n minus 1 with respect to a weight function Wx over the interval A and B. So this is what I get. So if I have if I have to get this, what should I do? Let me use the definition of dn by dx. So G of R of x Wx dx. So that's the integral. Okay. So this integral is done by because I have the formula that P of x is equal to 1 by Pn x equal to 1 by Wx dx to the power dn dn by dx to the power n Gn of x. Okay. So the Wx. So this is going to be A to B dn Gn x power of x dx. And how do you integrate these kinds of functions? The way to integrate it is you have to integrate it by parts. I suppose you know how to integrate by parts. So the integration by parts is the following. See, you know that duv, okay, is equal to u prime v plus v prime u. or v prime dv plus sorry, is equal to u dv plus v du, right? So I can take u dv is equal to duv minus v du, okay? Or I can integrate this one as integral u dv. This thing is integral duv a to b minus v du. Well, this is an integral. Integral a to b v du. So this is equal to uv a to b minus of integral a to b v du. Okay. So I use this formula and I want to evaluate dn integral dn by gnx rx dx. Okay. So what I'll make sure is that this I treat as u and this I treat as v dv rather. So if I integrate dn by integral a to b, if I were to integrate this thing dn by dx to the power n, let me not put the limits. Some function g of n dx is actually dn minus 1 upon dx to the n minus 1 gn, right? Because integration is the opposite of differentiation in some sense, so it will reduce the differentiation. Get here using the formula is that dn minus 1 upon dx to the power n minus 1 g of x r of x minus, this is between a and b, minus integral a to b dn minus 1 gn upon dx to the n minus 1 d by dx r of x dx. Okay, so now I have the condition that dn minus 1 that a equal to 0 equal to dn minus 1, here let b equal to 0 because this is the condition that we have. Okay, so gn minus 1. So when you put that condition, what you will get is integral a to b dn upon dx dn gnx rx dx is equal to 0 because the first term is 0 minus integral a to b d to the power n minus 1 gnx by dx to the power n minus 1 d by dx r of x dx. Is that clear? Just integration by parts. Okay, and the first term will be 0 because of the boundary conditions that we have imposed. Now let us look at the second term. So what is the degree of the polynomial if Rx is of degree p? Then dx. What is the degree of the polynomial when you differentiate it once?
Less than or equal to n minus 2.
No, if Rx is of degree P, then d by dx Rx is of degree
P minus 1.
P minus 1, because every time you differentiate, you reduce the power of x by 1. Okay, so what we have is we get this one. So if you keep repeating it, keep repeating. So when you do that, the end you'll get b dn upon dx gnx rx dx is equal to minus 1 to the power n integral a to b gnx di dx to the power n r of x dx, right? Because every time you integrate it, the next time you integrate it by parts, this one will become n minus 2. And this will become d squared upon dx squared. And what I have is a boundary condition which will give me gn n minus 2 at A minus of gn n minus 2 at B, which is 0. Because gn n minus 2 differentiated at is 0 at the two boundary points. That's the boundary condition that I have imposed. Is this clear?
Sir.
Okay. So now what I'll do is degree of d by d say p minus r 0 or p minus r or 0 if p is less than r. Right? Because supposing rx were to be x cubed and n was 4. Okay, d to the 4 by dx to the 4 of x cubed is going to be 0. Okay, so this is actually p minus. Okay, so anytime, so what happens is that this implies that the differential of r x goes to 0 if the power of polynomial degree of r of x is less than n. Because if it is less than n, dn by dx to the power n r of x is 0. Okay, so what I'll get is the right hand side will be 0, and so I have proved that phi n x is orthogonal to all polynomials of degree less than n. Is this clear? Is it clear?
Yes, sir.
So, this is the general formula. I will talk about some classical orthogonal. In a classical orthogonal polynomial, what GN is supposed. GNX is given by W of x times G of x to the power n, where G of x is a quadratic polynomial. That means g of x is equal to alpha plus beta x plus gamma x squared. Okay, so if I want to know the generating function Gn of x for say n is equal to 4, or x is equal to wx alpha plus beta x plus gamma x squared to the power 4. Okay. Hello.
Yes, sir.
Yeah. So this is what I have: alpha plus beta x plus gamma x squared to the power 4. Okay. And the examples are, for example, if you want to wx1 interval a comma b is equal to -1 to 1. Then we have the generating function g of x is equal to 1 minus. Okay, so I'm just doing it here. Yeah, and similarly, you will have this thing. This is for the Legendre polynomials. Okay, and similarly, you can show that for a Hermite polynomial. And all similar functions. So, okay, can you obtain a general differentiation for the polynomial? Point is, it's quite easy to get. So I'll show you how to get them. So let us consider the following. Okay, you consider the following term: d to the power n plus 1 by dx to the power n plus 1 times d by dx w g to the power n. Okay, so w is a weight function. Okay, and g is a quadratic polynomial. Polynomial of second degree. One way of doing this is just straightforward differentiation: Tn plus 1 upon dx to the power n plus 1 w g d by dx w g to the power n. So this I can write as a follow. That is g times, I can take g out, and dn plus 2 upon dx minus 2 wg to the power n. That will be the first term. I treated g as a constant. Everything else as the variable to be differentiated. Okay, and the second term that I get is n plus 1 times g prime. Okay, times n plus 1 upon dx to the power n plus 1 w g to the power n. Okay, and the third term that I'll get is where I differentiate n g twice. So I'll get n into n plus 1 by 2 into d into d to the power n and wg to the power n. Okay, and can you continue further? You see, because whenever you are differentiating, there is what's called the Leibniz rule. Okay, so supposing I am going to differentiate function n times. Okay, I'll say dn by dx power n. Okay, so this actually you will have the following. So you'll get f dn by dg or dn by dx to the power n g yeah. Okay, plus nc1 df by dx dn to the power minus 1 by dx n minus 1 g plus nc2 d squared f by dx squared d n minus 2 by dx n minus 2 g plus etc plus df dnf by dx to the power n times g. Okay, so this you can actually verify by first this is differentiating fg with respect to x once, and then differentiate it again with respect to x again, and so on, and then you can get the general formula. You can show that this is what you get by induction. Okay, any doubts? So I have used that, and what is what I have said is g prime is equal to dg by dx. G is equal to d squared g by dx squared. Now, because I have n, which is pretty large, maybe, okay. So, what happens to g triple prime? In the case of classical orthogonal polynomials, what happens? I'm given g of x is alpha plus beta x plus gamma x squared. So, what happens to d cubed g by dx cubed?
Becomes 0.
Okay, so it is only non-zero until the second differential. Beyond that, it is all zero. Right? That is why in this expression here, I have stopped at g double prime. Okay, you don't go any further, and I am differentiating n plus 1 times, as you see here. So when I differentiate n plus 1 times, then I'll get, instead of n here, okay, I'll get n plus 1 g prime dx and dn plus 1 by dx power n plus 1. And here instead of my nc2, I'll get n into n plus 1 by 2, that is n plus 1 c. Okay. So any questions so far? This is straightforward, right? So actually, you can write it. So one way of evaluating plus 1 by dx power. Okay. What is it? So g d by dx wc g d by dx wg to the power n. Okay. So as the following can be rewritten. See, I can use the following. I can use the following formula: dn upon dx to the power n, wg to the power n is equal to ys, because equal to w Okay. See, I had 1 upon W, dn upon dx to the power n, wg to the power n was equal to y. This was the orthogonal polynomial. Okay. So I say that W times Pn is equal to Yn equal to dn upon dx to the power n wg to the power n. Correct? I've just written the nth differential of wg to the power n as some function yn. Okay, if I do that, then yeah. So this will give me g times yn double prime, because this is dn plus it has d squared by dx squared dn upon dx to the power n wg to the power n, or dn upon dx to the n wg to the power n is yn, so it will become yn double prime. Okay. Plus n plus 1 g prime yn prime. The second the third one is yn. Different primes. So that same thing I have rewritten in a notationally simpler form. Okay. Now there's one more way you can actually evaluate this dn plus 1 from dx to the power n plus g times d by dx. D by dx w times g to the power n. Okay, I can differentiate g to the power n is nothing but w prime g to the power n plus n times w g to the power n minus 1 times g prime. Because d by dx gn is n g to the power n minus 1 g prime. Okay, and the first one we have taken g to the power n as constant and differentiated the weight function. So you get w prime. Right? It has w this thing w prime g to the power n dn upon dx to the power n plus 1 g times this plus n w g n minus g prime. To deal with. So what we will do is the following. So you know the definition of phi1, the first degree polynomial. What will be the first degree polynomial according to some? But x d by dx wx g of x, right? So I can write it in the following fashion. I can write it as w of phi1. Okay, for the notation simplicity, I have removed the x implicit. I've used it implicitly. So I get this one to be w prime g plus wg prime, or w prime g is equal to W minus G. Okay, so I can write this I can write as Dn plus 1 upon dx for plus 1 G times W prime to the power n. I can write it as W times P1 minus G prime times G to the power n minus 1, because one of the G's I have taken here, GW prime is what I'm replacing by. So this power now becomes n minus 1. Okay, plus NW G prime G to the power n minus 1. Right? Or I can write it as Dn plus 1 upon dx to the power n plus 1 Wg to the power n times P1 minus G prime plus Ng prime. Right? I guess is that clear?
Yes.
Or I can write it slightly in a slightly different form. Simplified one more step. Wg for n times P1 plus n minus 1 times G prime. Okay, is this clear?
Yes.
Okay, now as before, I will take I will differentiate this by terms. Okay, so the first by using the Leibniz formula. So what I'll get is the following. I'll get this one to be d by dx. Okay, d upon dx over n times w e power n to p1 plus n minus 1 g prime Okay, so I have just written it slightly separately. Okay, so if I do this, I can now differentiate. So when I differentiate, what do I get? Let me go through methodically. Tricky. Do it up, and it's pretty bad. So what I will do is I will again take dm by dx to the power n w g to the power n with yn. So I can write it as d by dx of yn times yn times p1 plus n minus 1 g prime. Right, but it becomes much simpler to write down. So what this gives me is yn prime times p plus n minus 1 g prime. Let me see whether I'm going to screw it up somewhere.
It was in product form, so how can we just separate omega wg?
Oh, and that's what you are right. I cannot do that. So that's what I said. I must have screwed it up. Okay, so I cannot do that. I will use it later on. Okay, so what I can do is I can differentiate it. So, I can't do it. Okay. So if I differentiate it, then I have this will be giving me dn plus 1 on dx power 1 plus dn plus 1 dx power n plus 1 wg to the power n n times n minus 1 g prime. Okay, so the first one will give v1 times dn plus 1 upon dx to the power n plus 1 wgn plus n plus 1 times p1 prime into p of dx power n wgn, correct? The first term is not giving more because p1 is of degree 1. Therefore, p1 prime is equal to constant and p1 double prime is equal to 0. So I cannot differentiate p1 more than once. If I differentiate it more than once, I'll get a 0. So the first term that I'm going to get is only p1 dn plus 1 by dx to the power n plus 1 wgn, and the next one is n plus 1 p1 prime. Why did I get n plus 1? N plus 1 into n minus 1. This thing, wgn plus n plus 1 p1 prime times dn by dx power n wg power n. Because I have got to differentiate this one once. So by using the Leibniz rule, I'll get the n plus 1 term. Okay. And what will I get from the second one? Plus d by dx dx. I'll write as n minus 1 g prime into d by dx dn upon dx power n wg, right? So there will be one term plus n minus 1 into n plus 1 g double prime into dn upon dx n wg power n. Okay, for the same reason as this one, g1, g is g and g prime non-zero, g prime and g double prime and g prime are non-zero, but g prime is equal to 0 because the polynomial d cube g by dx cube, that's going to give me 0. So this is all that I'll have. So this I can write it in the form p1 into p by dx. I have said defined dx to the power n by dn by dx to the power n w times g to the power n as yn plus n plus 1 p1 prime yn plus n is g prime d by dx yn plus n minus 1 into n plus 1 g double prime yn. So I'm never good at this. So this is going to give me P1 plus minus 1 to n plus 1 G double. Okay, n plus 1 n minus 1 to n plus 1 G double prime. There's no n. I'm taking n minus 1 plus n minus 1 G prime times yn prime. Okay, plus n minus 1 into n plus 1 G double prime plus n plus 1 prime yn. Okay, or I can still simplify further. I will get P1 plus n minus 1 G prime yn prime plus n squared minus 1 G double prime n plus 1 P1 prime yn. So this I have to equate to the way I have actually obtained it the first time around. So the first time around I got it as the following: G times yn double prime plus 1 times G prime times yn prime, right? Plus n into n plus 1 by 2 times G double prime. Okay, if you go back and see it, this is what I got. Show you. See, G yn double prime plus n plus 1 G prime yn prime plus n into n plus 1 by 2 G double prime yn. Now I can simplify it a little bit further, and I can write it as G yn double plus yn prime into n plus 1 prime minus of G1 minus of G prime, right? Because I've taken that to the right hand side, plus n into n into 1 2 square 1 minus n plus 1 P1 prime so I have yn has a coefficient. I have to take minus n squared minus 1 G double prime. And here I have n into n plus 1 by 2. That's also G double prime. Okay. Then I have minus n plus 1 P1 prime by n. So this is equal to 0. So I can say G y plus n prime into 2G prime G1 plus, so n into n plus by 2 n squared plus n by 2. So this whole thing will become n squared by 2 plus n by 2. Okay. Minus. So this will be n squared by 2. So this will be minus n squared by 2, and this will be plus n by 2. Then I'll have plus 1 times G double prime minus n plus 1 P1 prime yn equal to 0. Or I can I can yn prime plus g double prime to n where is a plus at the minus direction. Minus g squared into n squared minus n minus 2, the whole thing divided by 2 plus n p1 prime is the differential equation that is satisfied by classical orthogonal polynomial. Okay. Any doubts? It's very simple but cumbersome algebra. Okay, so G is actually a quadratic function, alpha plus beta x plus gamma x squared, and phi1 is a polynomial of degree 1. Okay, and then you will have n is a degree of the polynomial, and yn is actually the weight function times the orthogonal polynomial phi n of x. Okay, so in this, remember that yn is equal to wx. Okay, any questions? Any questions?
No, sir.
You can look at it a little more leisurely and then you'll find out more. Okay? So now, let me get sorry. You remember that earlier we had this thing, we had a 3-term recurrence relationship. Okay, it actually gave you x p and x is equal to x p n minus equal to k n minus 1 upon k n p n x minus or plus k n minus 1 p n minus 2x plus n p n minus 1x. Okay, so this is what we had for the 3-term recurrence relation. So similarly, I can get a differential recurrence relationship, and for obtaining the differential recurrence relationship, what we will do is we will start with a particular polynomial h of x has this form. G of x p n prime x writing still. G of x p n prime x minus of n by 2 x p n x. So What is the g of x given by? In general, alpha b x. Okay. So Pn is usually given by Kn x to the power n plus etc. etc. Okay. So if I take K this thing Pn prime, this will be n Kn x3 n minus 1 plus etc. etc. Okay. So I take G of x, so the cause is less than x3 minus 1. Okay. If I take Gx Pn prime x, what do I get? I get the leading term will be n gamma Kn x power n plus 1 plus some Cn prime x or Dn. English has enough alphabets. So the leading term of and you have minus x Pn prime x will actually be g of x Pn prime x, sorry, not the other one. Okay. Now let me. This is the first term. Okay. So the leading term, the first one is n gamma k to the n. N gamma k and x to the power n plus 1 is the leading term. X to the power n plus 1. And what happens in n by 2 g double prime x Pn. So g of x is equal to x beta x gamma squared. So g double prime is equal to 2 gamma. Is that clear? So this will have n by 2 into 2 gamma into Kn x to n plus 1 plus x to n plus 1. Yeah, I think it is clear, so I don't have to worry about the notation part so much. So what is the leading term here? Is n gamma Kn x to the power n plus 1 plus something in Gn minus 1. Let me know. I think this one has a problem. Beyond 1 hour, probably it's down. Okay. Plus some L n x n minus. So if I take the difference, I take gx Pn prime x minus n by 2 g double prime Pn x. So polynomial. What is the order of the polynomial? X to the power n plus 1 will go. Okay, so And if I multiply this by x, of course, I have x to the power n. It's not x. Okay, so what will be the order of this polynomial? See, if I go from phi n to phi n prime, I reduce the polynomial degree by 1. So the polynomial will be n minus 1. If I multiply by gx, because it has got an x squared term, the polynomial will be of degree n plus 1. So if I subtract one from the other, what is the leading term in gx pn prime x? What is the leading term? X to the power n plus 1. What is the coefficient in gx pn prime x?
N gamma kn.
This is the one, right? And what is the leading term in n by 2 g double prime x pn?
N gamma kn. Then
So what will happen when you subtract?
cancel. They will cancel each other.
They will cancel. So x to the power n plus 1 does not appear, right? So this is a polynomial of degree n, right? So I can expand h of x in terms of orthogonal polynomials. So I can say nu 0 n alpha nu p nu. Okay, and h of x. So if I want to find out is equal to h of x comma phi k of x, I have to integrate. So this is going to be sigma over nu is equal to 0 to n alpha nu p nu comma p k, right? And since this is equal to delta nu k, so this will give me alpha k. Okay. Now let us see alpha k is non-zero. So hx gx pn prime x, okay, minus of n by 2 into g double prime x xpn. So this was h of x, right? So h of x comma phi k of x is equal to gx pn prime x, gx into pn prime x comma phi kx plus g double prime into x n of n. Is this clear? Any doubts? Okay, the first term is going to be nothing but integral a to b, okay, pn prime of x pkx dx dx, okay, and the second term is going to be minus n by 2 g double prime into b. I can write it as x pk of x, okay, and k can take values from 0, 1, 2, etc. up to n, because h of x is a polynomial of degree n, so it cannot be expanded to anything other than 0, 1, 2 to n. You can't have coefficients corresponding to k. Okay, any question? So I can actually write it as integral a to b. Okay, so integrate by first term. Okay, so when I integrate by part, I will get P and d by dx, g of x, w of x, k of x dx. Again, I can write it as equal to, this will be with a minus sign because it's integration by parts. And I have also used the fact that G satisfies the boundary conditions so that I can integrate it again. P and x, and I can take W h x as d by dx. Let me do it a little more. Okay, I'll write as P and x. I will take Wx outside, then write as P pk prime Wx. That's the first term. That is, I have this sets together. Differentiated. I have taken Wx, and the next one will be wait this also. Okay, and the next term will be minus of integral a to b px gx pkx w prime x. Okay, so all I have done is integrate by parts, and I use the condition that if I integrate by parts, this is what I get. Now let me see how I can simplify it. Okay, so this will be minus integral because Ga is a polynomial of degree k plus 2. If I differentiate it once, it will become a polynomial of degree k plus 1. This multiplied by wx dx, that's the first. And then I had one more thing, that is, I had g times w we said was equal to y1 times, rather p1 times w. You remember that expression that is really awful. this G1 times W prime G I had was W times P1 minus G prime, right? W times P1 minus G prime. So I can put this as minus integral P and X. W prime G, I can write it as P1 minus G prime times PKX dx. Now tell me, for what value will these integrals be non-zero? If k plus 1 is less than or equal to n minus 1, equal to 0. Correct? Because phi n x is orthogonal to all polynomials of degree less than n, which means if k plus 1 is less than n, which is k plus 1 is less than or equal to n minus 1, then the first term is 0. Similarly, P1 minus G prime, this is a polynomial of first degree. Because P1 is a polynomial of first degree and G prime only has a linear term in x. Because if you differentiate alpha plus beta x plus gamma x squared, then G prime will just be nothing, will be nothing but beta plus 2 gamma x. Okay, so this one will also be of degree k plus 1. So this one is of degree k plus 1. Okay, this is clear.
Yes, sir.
Because G phi k prime is some function with a leading term which is x to the power k plus 2. So you differentiate it once, you get x to the power k plus 1. So it's a polynomial of degree k plus 1. So which means only non-zero terms on the right hand side. Alpha n, alpha n minus 1. Okay? Because this is what I was evaluating. Because I was evaluating alpha k, okay, which was actually inner product of h of x with phi of k, and h of x was the degree n. So k could only be a degree less than or equal to n. But now I have shown you that k has to be of degree greater than or equal to n minus 1 if it has to be 0, because of the orthogonality of the polynomials. Therefore, what we have, Pn this is equal to some alpha n Pn plus alpha n minus 1 Pn minus 1 of x. Or I can say that G one second, let it move. Or I can say Gx Pn prime is equal to some constant, some n by 2 or you can take a differential of c upper pi, which is 2 gamma, or that's one. Is going to be n gamma x plus some sigma n. Next, plus maximum x. So this is called the differential recurrence relationship. So it's extremely important when you want to say find out the momentum of state. What is the amount of data? I want to find out P. This is P of x, let us say, minus h cross by I, L by del x. Okay. So is equal to minus h cross by I integral over all space, whatever it is, minus infinity. Then you have psi by del k. So psi k of x del by del x, psi k of x dx. So if psi k of x happen to be orthogonal polynomials, then you can use this del by del x psi k x, which is as a linear combination of k and k minus 1 with x times k and k minus 1. You will be able to get the integration done very easily because you would know the normalization constants of the orthogonal polynomials. Any questions? Any questions? Yes or no?
Sir, it is minus h cross by I or h cross by I?
It is minus h cross over I del by del x. Rather, it is plus h cross. Okay. It's either minus h cross or plus h cross over I. There's a momentum operator is h cross over I del by del x. Okay, any questions on orthogonal polynomials?
No, sir.
So in the case of orthogonal, what it was, use x squared, etc. Generate and obtained the orthogonal polynomials. Previous n minus 1. If you are using the moments mix. And then what we did was we did a three-term recurrence relationship that we had. It's called real, distinct, and lie in the interval. So first of all, we started showing that how functions are just generalizations of vectors. Okay. So and then I showed you and then we obtain from Rodriguez formula the differential equation. So you now know three ways of actually dealing with polynomial: value of differentiation, or 1x squared, etc., being orthogonalized using a weight function and an interval a comma b, and then using the Rodriguez formula. Okay, so these were the general ways by which we did that. Now let me discuss something slightly different. So far, we use the one cos x, cos 2x, cos 3x, etc. These also are normal for the interval 0 to 2 pi, right? Because supposing you want to integrate integral 0 to 2 pi, okay, sine nx sine mx dx. So this is equal to some constant times Ln. Similarly, 0 to 2 pi x dx is also some constant delta Ln, and integral 0 to 2 pi sine nx is sine nx dx is equal to 0. Integral 0 to 2 pi cos nx dx equal to 0, and integral 0 to 2 pi cos nx sin nx dx is also 0. Okay, so we see that the cosine functions and the sine functions also form an orthonormal set, but the interval is different. It is 0 to 2 pi. Okay. Is it possible to express functions defined for 0 to 2 pi in terms of trigonometric functions, terms of and cosine of functions? The answer is of course yes. Okay. Yes. And what are these series called? When you expand a period function or function of 0 to 2 pi in sine and cosine functions, what do you call that series?
Fourier series.
Yeah. Yes. These are Fourier series. So what I'll do is in the from the next lecture onwards, I'll be dealing with Fourier series to some extent, and then deltas. Okay, and then I can go back to I think spherical harmonic, which is actually associated Legendre polynomials, and it is the IMP product. They are very important for chemistry purposes, so we will discuss those things. Okay, so right now I have given you an introduction to orthogonal polynomials. Next, I'll deal with Fourier series. I think I'll stop here. It's almost time. Okay, and we will continue from here on Monday. Okay. So, any questions? Any questions? So it looks like many people have gone home. Anyway, they have the video if they want to look at it. Okay, so I will log out. Okay.
Okay, sir.
Okay, bye then.